Hello everybody, and welcome to this lecture on common ion effect, selective precipitation, and mostly applications in qualitative analysis of both these concepts. So, as you know, chemical equilibrium is like a meeting place between chemical thermodynamics and laboratory practical experience. So this is where actual application of chemical thermodynamics takes place. In this regard, it is important to apply both these concepts, that is common ion effect and selective precipitation, and see how they are useful in our laboratory experience. So what we will do, we will try to use this in qualitative analysis of cations. See, if you are given a mixture of cations, cations are divided further into 6 groups: group 1, group 2, group 3, group 4, 5, 6, right? 6 groups that they have been divided. So we want to know the given cation belongs to which group. So we conduct few chemical methods and tell for sure that the particular cation is from this group. So how do we do that? So let us go further. Before that, let me reiterate what is a common ion effect. So just so that we are all on the same page, I will just write the definition of, it's there in the previous video. Even then, let me just this common ion effect. The suppression of the dissociation of a weak acid or a weak base on the addition of its own ion ions is called common ion effect. Basically, it's the suppression of dissociation. Means your dissociation is decreased because you added a common ion. Okay. So common ion effect is a consequence of Le Chatelier's principle. Another concept that we apply is selective precipitation. So compound with lower solubility product gets precipitated in preference to other compounds. Okay, so both of these will apply in qualitative analysis of cations. Okay, let us see for group 1 cation. Group 1, the cations are Ag plus Hg 2 plus Hg2 plus and Pb 2 plus. The group reagent is dilute HCl. Precipitation reaction is Ag plus when it reacts with HCl, you get AgCl, a white precipitate, plus H plus is evolved. Similarly, Hg 2 plus when it reacts with HCl, you get Hg2Cl2 plus 2H. So again, this is also your white precipitate, and so is with Pb2 plus, lead 2 plus with 2Cl minus, you get PbCl2. So this all thing. So the reason is, why do only these get precipitated? See, AgCl, HgCl2, Hg2Cl2 and PbCl2 compounds. So these have lowest solubility product. That is halides of Ag plus, Hg2 plus and Pb2 plus. Then further group cation chlorides. So if you want to know the values, for example, solubility product of PbCl2 is 1.6 into 10 to the power of minus 5. Solubility product of Hg2Cl2 is 1 point. You need not know these values, just it is for you to understand how low the values can be. AgCl, it is 1.7 into 10 to the power of minus 10. Okay, so since you see minus 5, minus 18, minus 10, which means they have a very small solubility product. So halides of first group gets precipitated in preference to the halides of further group cations which remain in solution. So the halides of other solution, the cations, halides of further group cations remain in solution, while these halides AgCl, Hg2Cl2 and PbCl2, because they have very small soluble product, they get precipitated. That is how you can separate out and tell that, okay, if some precipitation is happening in this first group analysis, you know it is the cation is among these three, and you can do further confirmatory test to decide which one exactly is it. Okay, now let us go to the group 2 cations. So which are all the cations? I'm just giving few of them, I'm not writing entire. So Cu2 plus, okay, Cd2 plus, again Hg2 plus, bismuth 3 plus, SN4 plus. So these are all the group cations. The group reagent is your dilute HCl. Dilute HCl and H2S gas. So what are the precipitation reactions happening here? In presence of HCl. Okay, what is the reason? Why do sulfides of group 2 cations get precipitated here? So this is your reason. So the sulfides of second group are having lower KSP, lower solubility product than sulfides of further group cations. Hence, sulfides of second group get second group cations get precipitated in preference to sulfides of further group cations. Further means group 3, group 4, group 5, group 6 cations which remain in solution. So for example, if you take the solubility product KSP of copper sulfide, it is, you know how low, it is 8.5 into 10 to the power minus 36. If you take CDS cadmium sulfide, it is 3.6 into 10 to the power of minus 28. Very low solubility product. That is why these get precipitated in preference. Okay. Now, why is there a need to add HCl? What is the role of HCl here? Why should group 2 analysis be done in presence of acid? Can you justify that? The reason is why HCl is added. Now, as sulfide precipitates of second group cations are having low solubility product, so what happens? So ionization is carried out in presence of dilute HCl, which gives so ionization of H2S will give you 2H plus H minus. Now ionization of HCl will give you H plus and Cl minus. Now because of this common ion effect, see here H plus and H plus, what will happen is, and Le Chatelier's principle, whatever you try to do, the system will try to undo that effect. So which means equilibrium here shifts to left. So due to common ion effect, H plus, the concentration of S2 minus is decreased. Okay, so ionization of H2S is suppressed, cations. Okay, so what will happen if we don't add HCl? See, there are further group cations like Mn2 plus, which do not belong to second group, zinc 2 plus, nickel 2 plus, cobalt 2 plus, now whose solubility products are, for example, for cobalt sulfide, nickel sulfide, manganese sulfide. Here the KSP is 4 into 10 to the power of minus 20. Okay. So if we don't add HCl, without the addition of HCl, if you take the ionic product H plus and hydrogen sulfide, just due to hydrogen sulfide, the KSP is around 4 into 10 to the power of minus 10. So which means because these are also lesser than the ionic product of H plus 2 and H2 minus, just the H2 minus, these also will get precipitated. But when you add due to common ion effect, this is just H2S. Okay. Due to common ion effect arising out of H plus, that is from HCl, the solubility KSP is brought down to 10 to the power of minus 30, which is just sufficient for precipitation of group 2 cations. So only group 2 cations will get precipitated. If you do not add HCl, group 3 cations will interfere and get precipitated. Now let us go through group 3 cations. So which are the cations here? So iron 3 plus, Al 3 plus and chromium 3 plus. The group reagents are NH4Cl and NH4OH. So what are the precipitation reactions? Three plus ammonium hydroxide in presence of NH4Cl will give you iron hydroxide. So the hydroxides of 3A group are having lower KSP values than further group cations. Hence, hydroxides of third group get precipitated. Get precipitated in preference to further group cations, okay, which remain in now. Why do we add NH4Cl? So listen carefully. The hydroxide precipitates of third A group are having low Ksp values, which means the amount of hydroxide ion required for precipitation of these cations is very less. Hence, ionization of NH4OH, ammonium hydroxide, is carried out in presence of ammonium chloride, which gives ammonium NH4 plus as a common ion. Now, due to common ion effect of NH4 plus ion from NH4Cl, the ionization of NH4OH is suppressed, which limits the concentration of OH, and this limited concentration of OH is just enough for complete precipitation of third A group cations. So, this is again common ion effect at play. So, ammonium hydroxide. And when you do it in presence of ammonium chloride, so this is your common ion. Okay, so this was your so next we'll move to group 3B. So what are the cations here? CO2 plus, Ni2 plus, Mn2 plus, Zn2 plus. What are the group reagents? Ammonium chloride plus ammonium hydroxide and H2S gas. Okay, we'll come to know why H2S is added here. What are the precipitation reactions? So Zn2 plus reacts with H2S in presence of NH4Cl plus NH4OH to give zinc sulfide plus PH plus nickel 2 plus plus. So here what happens is, what is the reason is why these are the group reagents is the Ksp values of sulfides of group 3B. This is important. So I'll just write it down. The KSP values of sulfides of third B are relatively high. So hence amount of sulfide ion required for precipitation of cations are very high. If this precipitate of third group is carried out in presence of NH4Cl and NH4OH, what happens is ammonium chloride will ionize as NH4 plus Cl minus. NH4OH will ionize as NH4 plus and OH minus. Okay, and H2S is ionized as 2H plus S2 minus. Now what happens is this H plus and this OH minus will combine to form water. Okay, now since H2S is used up, what does the Le-Chatelier's principle tell? If this is used up, what will happen? The equilibrium here will shift towards right. So Le-Chatelier's principle, more of H2S dissociates, S2 minus ion concentration increases, which are sufficient for complete precipitation of cations. Now why did we add NH4Cl? To suppress the ionization by common ion effect, the concentration of OH minus to suppress the ionization of OH by common ion effect of NH4 plus, no, not NH plus, and thereby decrease the concentration of else hydroxides of Further, group cations may also be precipitated. Okay, so this is enough for your understanding of qualitative analysis. We'll not get into group 4, 5, and 6, so they are very simple. So this should suffice. So make notes, ask your doubts, and thank you. All the very best. See you all.